Hi, kids. We're gonna go over the Universally Yours, simulation lab where you determine the universal law of gravity. So first, a little bit of background. So let's say we have the Earth. Okay, there is the Earth. Okay, and we have an astronaut. There's my astronaut. Okay. Obviously not drawn to scale because that would be way, way, way too big. And our astronaut is in a spaceship. Okay, and the spaceship is orbiting the Earth. Okay, and I think everybody's pretty familiar seeing pictures of this. That hey, the astronaut floats around. And if you were to ask most people, well, why does the astronaut float around? In fact, this was your question, and maybe you said the same. Well, most people would say, oh, well, the astronaut floats around because there's no gravity there. But then if you were to ask that same person, why does the spaceship orbit the Earth? They would tell you gravity. In fact, if you had like, now this is definitely not drawn to scale. Here's the moon. If I wanted to draw this to scale, I would have to draw this way, way, way off to the right. But there's the moon. In fact, if you were to ask the same person, like, well, the moon goes around the Earth, right? Yeah. Well, why does the moon go around the Earth? They would say, oh, because gravity's holding it there. Yeah. So does it make any sense that there is no gravity uh, acting on this astronomer, or there's sorry, this not the astronomer. I guess it could be astronomer on the astronaut. No, that doesn't make any sense. In fact, on the space station, if here's the Earth and you were to just draw where the space station it actually is, it's like super close to the surface of the Earth. That you weigh about 90% of what you weigh, like your weight is about 90% of what it would be on the surface of the Earth. So to say, oh, there's no gravity there, that's just not true. Okay? So keep that in mind. But in the simulation, you were supposed to do something like this. You had a 1 kilogram mass, okay? And then you had another random mass, which we'll just call M. You were supposed to set them so that the distance apart. Now, you'll notice I measured from the center to the center. That's really important, which is also why we're going to call this distance from the center to the center, we're going to call that R because it's really it's like a radius. Okay. But measured from the center to center, that was supposed to be 1 meter. And then you were supposed to graph. And you were supposed to then vary this mass and look at the force of gravity. And you were graphing the force of gravity. Now, hopefully you did this. The units over here were times 10 to the minus 11th newtons. Okay. And this was mass. The units of this was kilograms. So you varied this mass and you saw how that affected this. Okay. And when you graphed it, you should have got a line, which you already knew that because if you remember, if you're on the surface, you just said Fg equals mg. So m affects g. Duh. Okay. But I do want you to see that hey, this is still true. So you should have seen that hey, Fg is proportional to m, and if you do your y equals mx plus b, well, what did I graph instead of y? I graphed this, and you should have gotten that, well, let's just write it, y equals mx plus b. Instead of y, I graphed force of gravity, but remember, the units for that was times 10 to the minus 11th. Your slope should have been 6.67, and we'll talk about that later. And then x was really mass, okay? So far you should have had something that looks like that. Then you were supposed to do the same thing, except now you have a 1 kilogram mass and another 1 kilogram mass. And now remember, measuring from center to center, you are going to vary that distance r. Okay? And see how that affects it. So if you graph this, again, this was in times 10 to the minus 11 newtons. and then this was r measured in meters, and you should have gotten this. Okay, in this case, if you did it, you should have said that, hey, this is proportional to 1 over r squared, which, just so you know, that's the same thing as r raised to the -2. So the app probably said -2, but you're smart, right? Okay. And then, so if you had to linearize this, so you had Fg here times 10 to the minus 11th newtons, and then you put 1 over r squared there, and you got a line, and then you said, well, if I think about y equals mx plus b, my y was really Fg, measured in times 10 to the minus 11th. My slope came out to be that same number again, 6.67, and then x was 1 over r squared. Okay, so obviously this 6.67 is going to be an important number, and you're right, it is. Okay, so let's put it all together. If we put this all together, we would get, if I have, random mass 1, random mass 2, separated by a radius of r, you should have seen that, hey, you know what? Fg is proportional to m1, Fg is proportional to m2, Fg is proportional to 1 over r squared. Well, that means Fg is proportional to m1 times m2 over r squared. Okay, I'm just putting it all together. But we had that 6.67 number, and then this is where, if I was actually having Fg in newtons, I would actually have to write this equation, for example. It would look like this. Okay, times mass. So really it would be this equation, 6.67 times 10 to the minus 11th, because that was that constant, m1, m2 over r squared. And if you look on your formula sheet, you will actually see this, and we'll talk about why they write it like this. Okay, so on your formula sheet, you see it written like this. Fg is equal to g m1 m2 over r squared, where g is, again on your formula sheet, the gravitational constant, 6.67 times 10 to the minus 11th, okay, where g equals 6.67 times 10 to the minus 11th, okay? Let's talk about why they write it this way. So anytime the College Board puts an absolute value here, that is telling you that this is a lovely equation to find the magnitude of the force. So to find the magnitude of the force of gravity, you do this, okay? If you want to find the direction of the force of gravity, draw your FBD. Okay, so this equation will not tell me direction. This equation will just tell me the magnitude. Now, I will tell you, most of the time when I write the universal law of gravity, most of the time I'm going to write it like this. Big M, little m, r squared. And you might ask, well, why would I do that? Here's why. Most of the time, we are talking about something like, hey, here's the Earth, and here is a satellite orbiting the Earth, space station, whatever. Well, guess what? The Earth is my big M. That satellite is my small m. Okay? If you do it that way, it's going to make things way, way, way easier. Okay? Because it's going to be easier to keep track of, well, I have a little m, I have a big M, and canceling things out. Okay? That should allow you to finish, or hopefully that makes sense with everything that you're doing. Make sure that you are okay doing proportional reasoning stuff. And then the last thing I just want to mention, here's where, again, you got to be careful that R is measured from there to there. So if I say, hey, you have the Earth, and that's the radius of the Earth, well, you have something else that's a radius above the surface. What did I just do to R? Well, this is R and that's R. I just made R times 2. Well, look, if R is times 2, this is an inverse square relationship. If I take the inverse of 2, I get 1/2. I square it, I get 1/4. So if I am r at an altitude of r above the surface of the Earth, the force of gravity on that object is going to be 1/4 as big. Cool sauce. Bye, kids.